Hi, I'm Benny, and I've dedicated my life to understanding the universe, with the hope that one day I'll get the chance to hop on a rocket and see it for myself. Growing up, I was always looking up, not just at the stars, but at the endless questions they sparked. I'd spend hours wondering what was out there, how it all worked, and if I'd ever get the chance to see it for myself. This is Space Bites, where I take the overwhelming, mind-bending world of space and break it down into small, easy-to-digest pieces. Think of it like snacking on the cosmos, quick, simple, and deliciously full of wonder, so anyone can understand and enjoy it no matter their background. Why? Because every atom in your body was forged in the heart of a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it began in stellar furnaces, which means, quite literally, the universe is in you. You are the product of cosmic alchemy, billions of years in the making. The same processes that built galaxies also built you, linking your existence to the cosmos itself.
Hello, my name is Elias. I am a PhD student here at CERN, the world's biggest particle physics laboratory. What we do here is to collide particles almost at the speed of light. And we do this by taking particles. We remove all the electrons, we accelerate them in several steps, and we collide them in the Large Hadron Collider. So you could say that here at CERN, we actually have a time machine studying the few microseconds after the Big Bang. So it's the way to study these primordial conditions that we had in the very, very early universe.
Hello, everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. And today we're sitting down with Elias Waagaard here at CERN, actually. And together we're going to decode accelerator physics. So first off, how are you doing today, Elias?
Fantastic.
Do you want to explain where we are?
So we are at CERN right now. We're one of the top floors of the buildings here close to the first accelerators at CERN. So we just visited a few points like the antimatter factory, the synchrocyclotron, and the low energy ion ring. So we're in the Miran campus, right between the border of France and Switzerland.
Do you want to introduce yourself? Maybe tell me a little bit about your academic journey. What drove you to pursue a career in physics?
So I'm Swedish originally. So I come from a small coastal town in northern Sweden. And the universe and physics always fascinated me. I think the study of matter, the universe, I think this is a field that attracts a lot of curious people. And I think I've always considered myself very curious. And already when I was around 13, 14, I started participating in some space camps. And I went to an Aurora camp in northern Sweden. And I think that's what really sparked my curiosity for the universe and cosmology in particular. A few years after, during my first year of high school, I went here to CERN to visit these scientific sites for the very first time. And seeing all this with my own eyes, and this was 2013, when the Nobel Prize for the Higgs boson had just been awarded, was probably the height of excitement. Probably that triggered me to study physics at university. So I enrolled at the Uppsala University, do my bachelor's in physics there, and later on a master's in particle and nuclear physics. And then during my last year there, during my master thesis, I came here as a technical student to do my thesis work. So that was more numerical optimization, accelerative physics, and a bit of machine learning. And here I am today as a PhD student at the EPFL University in Lausanne, now focusing more on some ion beams, especially oxygen. So I'm at the last year of my PhD now, so now it culminates, you can say.
So should I call you Dr. Elias or
Not
just
yet.
Elias? Okay.
I had it in the thesis, but I still have to defend it.
And you mentioned that the Higgs boson was it was in 2013. It was a very important time in physics. Can you explain why for the people that are not familiar with this?
It was one of the last puzzle pieces of the Standard Model. So maybe many of you are familiar with the periodic table of elements, so describing different elements, helium, hydrogen, lithium, and so on. Now, there's one model, one level below called the Standard Model, which describes all the quarks and various leptons, so electrons, muons, for example. So the particles that make up all the protons and neutrons that build up the atoms. So that's the model that describes this visible matter that we see. And the Higgs boson was the last major, let's say, force-carrying particle, the last puzzle piece that we needed to confirm whether this was correct or not. And this had been predicted already, if I remember correctly, in the 60s, but it had never been observed like experimentally. So in 2012, finally they announced that they had discovered it with two different experiments, so ATLAS and CMS, at the Large Hadron Collider. Here at CERN, there's the world's largest particle accelerator. It's called the Large Hadron Collider, shared between Switzerland and France. and is run by CERN as a host institute. So with hundreds of nationalities, more than 10,000 people, and it has 4 major experiments on it. And what was special about this discovery is that 2 differently designed accelerator detectors managed to discover this particle, but through 2 different ways. So they can actually confirm and say this was the discovery.
Wow. Do you have a favorite particle?
I like the graviton.
Why?
Because this is the last, let's say, hypothetically existing particle that would mediate the force of gravity. So in the universe, we have 4 major forces. So we have the electromagnetic force, the one that we see every day with lights, magnetism. Basically, the fact that when I touch this table, I feel that it's a table. It's the electromagnetic repulsion. So that's the force that describes basically how we interact with matter today. Then we have the weak force, and this describes radioactive decay. And for example, in nuclear power plants and isotopes and radioactive material. Then we have the strong force, and this is carried by the gluon. So this particle basically glues together the quarks to form neutrons or protons or other particles. Now there's a 4th force called the gravity. And the gravity is the weakest force. Yes, it's the most important force at long distances. So what's interesting is that these 3 forces that I mentioned earlier, they can be described through quantum mechanics, so unified nicely in one theory. The problem is that gravity, on the other hand, is described today by Einstein's theory of general relativity. And this one does not fully agree with quantum mechanics in some cases. For example, they both describe black holes in different ways. So hypothetically, this graviton would be the final particle that would allow us to describe gravitational interactions, let's say, in the same formalism with the standard model. Problem is that we haven't found this particle yet. And maybe we will never, because the force is so weak, so it will be hard enough to excite this field and get the particle out. So it's my favorite particle because it's the last missing puzzle piece before we have a grand unified theory to explain all of the constituents of the universe.
So you say you're studying to become an accelerator physicist, like that's the correct term. So what does an average day for you look like? You walk into the office, what is the first thing that you have to do?
So 80% of my time I spend in front of a computer.
Mm-hmm.
So I work both with theory, numerical simulations, but also experiments. Most days I'm in front of my computer, maybe I have a piece of paper. And most of the times the machines that we work with are too complicated to be described on a piece of paper. So then we need computers. So we have big computer programs that numerically then describe all the components in an accelerator. So all the magnets, all the components can be described mathematically. So then we have to sort of, if we want to study a beam and how it goes through all these magnets, we then have to find a way to describe, to make a program that then sort of describes every step what happens to this beam in an accelerator. So that's what I do a lot of the time. So I run simulations. I try to predict how can we study this effect. Is this electromagnetic effect important? Will we see beam losses? But then some amount of my work I dedicate to experiments. Then we actually go to the control room. And then maybe I have some parameters that I want to check. Okay, if we change the number of oscillations per turn, or if we change the intensity, how will this affect the models? Like, is the model accurate? So basically, theory, trying to predict what's going to happen, then simulate it and say, okay, what will come out? And then you go into the control room and you, let's say, manipulate the beam and you see, are these models correct? So that's what I do.
It's very interesting.
But then, of course, I do a lot of outreach as well. So usually I guide groups, both from high school students ranging up to sometimes university professors that come and want to see CERN. So I do this every now and then. I also have a YouTube channel with some outreach videos of how it works at CERN. I've been pretty active in Big Science Sweden. So the industry liaison officers that, let's say, try to connect with Swedish companies, so the country that I'm from, and trying to tell them what is CERN and what can they do for CERN, for example. So for me, it's very important as well to let the rest of the public know, especially since they contribute with tax money to run this place.
I mean, that's what we're trying to do here at Space Bytes, is to try to make this as much accessible as possible. Can you explain what is meant by the term accelerator?
So accelerators, then, a series of magnets or electromagnetic radio frequency cavities that either steer or accelerate particles. So before accelerators existed, then when we wanted to study these high energy particles, we had to look at cosmic rays. So some 100 years ago or more, they went up with a hot air balloon in the atmosphere with a detector. So then they had basically some type of smoke chamber. And then they could see sometimes these particles coming in and out, which is nice, but it happens too rarely. And if you need a lot of statistics, if you need billions or trillions of events, it's not feasible to do this anymore. So if you want to be able to control the particle, the energy, type of collisions, etc., then to do this in a controlled way on Earth, you need a particle accelerator. Then you need to put your particles together, form a beam, accelerate the beam to the energy that you want, and then let them collide.
So that's what accelerator physics is.
The accelerator physics is then the study of how you accelerate and manipulate these charged particle beams such that we can create this collision. So we basically create a mini version of the microseconds after Big Bang. So in a nuclear power plant, for example, there we convert mass to energy according to Einstein's formula. In a particle accelerator, we do the opposite. We convert energy to mass. So we collide higher energy beams. And all this energy, some of it at least, is used to form new particles that are unstable, they decay. And then these big detectors that we build around them then can reconstruct this debris that comes out and see what was the initial collision, what particle was formed there. So in this way, we can actually study the conditions of the early universe, like microseconds after. So it's like a time machine here on Earth.
I like that metaphor. It's very cool. Have you ever had a moment at CERN that felt almost spiritual, like you were really touching at the edge of something very profound?
So there have been quite a few of those moments. I think, especially visiting all these sites for the very first time, I think especially having watched the movie Angels and Demons by Dan Brown, and I came into the antimatter factory for the first time. Dan Brown, he has written the Da Vinci Code, a few other blockbusters. And in this movie, the first scene takes place in this antimatter factory, and this sect wants to steal some antimatter to blow up the Vatican and take the eye of the physicist. They go in and then they steal the antimatter. I guess in theory you can do this. It's one of my favorite science fiction movies. Not always scientifically accurate, but it actually takes place here, the very first scene. Now, not scientifically, maybe not accurate, but the first security, let's say, breaching scenes where they try to go in and steal the antimatter is very, very realistic. So coming into this antimatter factory for the first time and seeing this by my own eyes, realizing, wow, this is the only place in the universe where we can, in a controlled manner, actually build this antimatter and study it. For me, that was like I felt so small in comparison to what there is. Because that's another mystery, right? Apart from this gravity versus quantum mechanics mystery, another big mystery is why is the universe made of matter and not antimatter? Because we know that antimatter formed after the Big Bang, but somehow it was annihilated because there was a surplus of matter, but we don't know why. In this antimatter factory, we actually study these things. And it's only a few hundred meters away from my office where they do this work every day.
So touching on what you just said, what questions are you personally trying to answer about the universe through being a scientist or through being a physicist?
So first, I want to highlight that here at CERN, everything is a team effort because we are thousands, if not tens of thousands of people working on these experiments. So everyone is an expert specialized into something particularly small. So in my case, I work with the accelerators. So we are the ones specializing in delivering the particles to the detectors. And then some theorists or data analysis specialists take over and study the collisions. Whereas in our case, we want to deliver as high intensity, as high quality beams as possible of various species all the way to the Large Hadron Collider. These particles have to be produced in a source, either a gas bottle or some crucible where sort of the solid is being turned into a plasma, then going through a linear accelerator, and then going through a sequence of smaller accelerators where each of them then accelerates the particle beam to higher and higher energy. Normally, for like 9 to 10 months a year, we use protons. But for 1 to 2 months per year, we use lead ion beams. So lead ions are much heavier. Instead of protons, 1 plus, we have 82 plus. So it means that we can, thanks to the higher charge, go to much higher energies. And we can create, in the particle collisions, something that is called quark gluon plasma. So we have solid, we have liquid, we have gas, but we also have plasma, but then we also have quark gluon plasma. So then the energy is so high that basically the gluons that are super strong, they're representing the strong force, are suddenly overcome by this high energy that everything is torn apart into a soup, quarks and gluons. So this is what happened really in the microseconds after Big Bang. So thanks to these heavier ions, we can actually create these really, really primordial conditions. So this is mainly what the Alice experiment, for example, that the LHC studies. Now in my PhD, I mainly address two problems then. A, with proton beams, we almost don't see any losses along the accelerator chain, relatively speaking. Lead ions, on the other hand, we lose 10 to 20 to 30% in each step. It is not fully clear why. So this is what I've been addressing in my PhD. And in particular, this year, we actually tried oxygen beams for the first time. Because with oxygen, the idea is that you can find some type of compromise between not having too much charge in the beam. Like more charge would mean that the beam sort of blows up in size. So then the quality degrades and you have more losses. So you would have to we would want a balance between as many nucleons as possible, as many particles as possible, versus then these defocusing, we call it space charge forces, for example, so electromagnetic repulsion. So to find like a sweet spot in between them. So basically I was asked in my PhD to A, understand why do we have these losses today with lead, B, how is this going to look like for oxygen? And since there was no operational experiment, there was very little material to start from actually. So I had to sort of build all these semi-empirical models, but also sort of detailed models of some accelerators from scratch.
And would you say it was mission accomplished? Have you achieved what you set out to do in the beginning?
So I hope so. Well, actually last year, so in November 2024, we reached, I think it was about 30 to 40% above the 2030 targets for the lead beams. So we managed to understand some of the loss mechanisms. We managed to compensate some of these things. One of the problems, for example, is that in an accelerator, you have dipole magnets to keep the beam on track, and you have quadrupole magnets to focus the beam. The problem is that these quadrupole magnets, they are connected to power converters, so to have the direct current in the magnet. They are connected through the AC current from the electrical grid, and you have these 50 hertz oscillations. And the problem is that if you have these 50 hertz oscillations, then these focusing magnets, they sort of oscillate in their focusing strength. So you will have some, we call it a ripple. So this ripple effect will then cause some of the beam to sort of shake in a way that we don't want to. So then by applying a voltage, just like noise canceling headphones, then you can sort of compensate for this effect. And this had been tested on some other beams, but never on lead ion beams. So we tested this out in 2024. So just like noise canceling headphones, we managed to correct for some of the most important frequencies. So there's 50 hertz, but also 150 or 300, so higher harmonics. So we managed to focus on 50 hertz, which was the most important one. And in this way, we could actually see these losses went down. And also the theoretical models predicted that this would happen. So it was a nice spot-on prediction that this would improve the performance. And this contributed to this almost 40% increase compared to the 2030 targets. So that was a nice thing. But then also for oxygen, the fact that we managed to deliver such high quality beams and some of these effects scaled in a way that we really expected. So it was sweaty because these things happened now in July, so a few weeks before I handed in my PhD thesis. But it was very nice to see these years of work and all the models, and then seeing where this would lead.
So why do you think it's important to explain to people that don't have a background in STEM the importance of the research being done here at CERN?
So there are two levels, I think. Well, actually three. First of all, we have the fundamental science itself. I mean, we are curious creatures. We want to explore and understand more of the universe. I mean, this is why we climbed the highest mountains. This is why we crossed all the oceans. This is why we've been trying to understand what is atomic physics, what is particle physics, what is chemistry. So just for the sake of knowledge itself, I think it has an inherent value just to understand why is the world around you built in the way it is. So I think this is the primary and fundamental reason why we do this. Like we want to understand more of the world we live in. The secondary, let's say, objective, I would say, is also to have all these spin-off effects. So by setting up these enormous accelerators and experiments, we also have some technological challenges. We have to store data, we have to build all this cable work, we have to set up all the computer infrastructure. And in this quest of setting up these systems, we also then discover new inventions that can be harnessed in industry, for example, the private sector, the public sector. I think the World Wide Web is probably the primary example. This was invented by Tim Berners-Lee here at CERN. Like back in the days, like in the probably 60s, then I have seen photos of people biking across the sites with the stacks of papers of all the results, right? But after a while, that's not practical anymore. So we need computer systems to transfer this information digitally. And in order to do this in a controlled way, then the World Wide Web and the HTTP, so the protocol that we all use today, were invented here. So then these secondary effects allow the society to benefit from all these things that we invent here at CERN. And third, I think CERN plays a very important educational role. So a lot of people, all the high school kids that I guide, all these adults, or even professors that maybe from other disciplines that come, they feel inspired when they come to CERN because you see that it's an amazing laboratory. So I would say it's threefold. It's the importance of the research that we do here.
I think that's a very nice way to put it. And do you feel like, whether, despite their age, if they're professors or children, do they come in with the same sort of like wide-eyed curiosity and passion for the science? Wow.
On average, you see that in almost everyone. Yeah. And then there are always probably I was one of those kids myself who was there always asking questions, being super excited coming to CERN because you're actually here, the place you've heard about from all the documentaries, videos. So working here has been a very big privilege.
So what is CERN?
So CERN is an international organization based in Geneva, in Switzerland, and it's a particle physics laboratory, the world's largest. And then it hosts a myriad of different experiments, including the world's largest accelerator, the Large Hadron Collider. So I was telling you before about how we create these time machines to create these primordial early universe conditions. And this is what we do here. This is what we need to do it. We need an enormous laboratory with all these talents, this expertise, all this technical infrastructure just to run these experiments here. So in addition to being the world's largest particle physics laboratory, it's also one of the largest laboratories overall, with all these hundreds of nationalities, thousands of people, with so many projects going on. So today we have more than 23 member states. I think some new ones came very recently, that all contribute with a certain percentage of their gross national income. So they all contribute, and they all have to be a part of deciding what are the next objectives, what are the next experiments going to be. So it's a big international physics organization.
Do you know what are the near future objectives of CERN? Are we looking for something specific? Are we trying to answer some specific questions?
So right now it's still not fully decided yet. In the next few years, the plan is that the next big accelerator is going to be decided which one to build. Right now the Large Hadron Collider is the largest, but this plan, including the present upgrade that is happening, it will only take place until 2045. After this date, we don't have, let's say, a clear plan yet. Some of my colleagues, they work on an accelerator called the Future Circular Collider. So this is a 90-kilometer ring that will go underneath the Lake of Geneva, around the mountains here, and it will be an unprecedented accelerator of a size that we couldn't imagine recently. The thing is, it's very big, it's very expensive. The host states could not afford it by themselves, so some other stakeholders will need to come in. And the idea here is to push the energy frontier further. But it would consume a lot of energy, it will take a lot of money, many decades to build it. So it's not fully sure whether it's going to be built or not. But my colleagues are working on a technical design report, so there are tangible plans.
So let's try to remove some of the myths about CERN, because I know that when they wanted to turn on the LHC or one of the other accelerators the first time, the general public was scared. They thought they were going to open a portal to another universe or a black hole or something. So let's debust some of these myths. What's like one common misconception that you hear a lot from people that you want to say, no, this is not true, this is not scientifically accurate?
So, well, first thing, black holes are not being formed here. Like in the best of cases, we can form new particles, but black holes, no. I mean, the thing with black holes is that you need a lot of mass concentrated. And we're talking about like not even atoms, but ions, so like small particles that we collide. So for a black hole to happen, I mean, you need many solar masses for this to happen. So I think it's more likely that this would happen somewhere else on Earth rather than at CERN. And I think we're not going to open up new dimensions. I think what, on the other hand, we do here at CERN is to just create energy densities that sort of are similar to microseconds after the Big Bang. But those only occur for a fraction of a second before they decay, and then we study the debris. So no black holes being formed here.
No portals to other dimensions. No. Wouldn't that be exciting, though?
I guess.
Is it scary or intimidating working at a place that is very high stakes, such as here? Because you also mentioned that there's a lot of security, there's a lot of safety precautions.
So here at CERN, if we talk about high stakes security, I think this is very important, because obviously these high energy beams, they can be very radioactive. That's one of the reasons why the tunnel is dug down to more than 100 meters below ground. So because while it's running, there are, let's say, tangential radiation coming out that's present when the beam is running. So then it's important that no one is down in the tunnel. So to have this security system is very important. I mean, no fatal accident has happened at CERN because of these tight security measures. And then you walk around and you see, wow, this is very important equipment. Maybe I shouldn't touch it if I don't know it. But as long as you stick to the security rules, it's fine.
And what is one thing that really surprised you about your time here at CERN?
Well, I think there are many things that surprised me. I think just from a technical point of view, the fact that it's so complex, so many layers, one on top of the other, of how things are controlled. You have the expert technicians, but then you have also many groups and departments, etc. So the organic size of this organization is just huge. So I think that was quite of a, let's say, a first impressive moment that I had when I saw this. I think another thing that surprised me when I came was that I came, but then to go down to the tunnel and to some of the points, like just to go down to the Large Hadron Collider, you actually have to do a gas mask training. So basically we had a mock-up tunnel where we did a simulation of a gas leak, and where they actually had smoke and coming out and so on. So it felt like a proper fire evacuation exercise. So then we had this World War I type masks that you have to be able to put on in 30 seconds. And I do a lot of scuba diving, right? So then there were some similarities of how you have to do this underwater. So once again, we come back to the security, etc. But we work with real machines and the most extreme conditions you can imagine, the highest energies, the coldest temperatures in these superconducting magnets, the strongest currents you can imagine for these high field superconducting magnets. So I think these technical aspects impressed me a lot. But then, of course, I think one of the major reasons why I came was also to meet all the people here. And I think that's what positively surprised me, to meet so many other young people that are curious about the universe. There are a lot of talents you can learn from.
And just to finish off, last two questions. My first question for you would be, if, for everyone that is listening, what is one message that you have, either about anything that you're passionate about, either it's about the physics or about the research, what is one message that you want to get across to people?
So I think one of the most important things that have guided me along the way is hard work. Talent is one thing, but ultimately it's hard work and dedication and also to some extent organization that will bring you far. So working hard together with other people for the right purpose has been very important for me. And I think at a place like CERN, you can work hard, especially during a PhD, because then you have a relatively vague project from the start. Maybe you don't even know exactly what the problem is. And then you have to work hard over many years trying to address these questions. And you do it with people, and there's this team effort. So I think I've learned a lot about how to become a physicist that I wanted to be here. And I think if anyone out there is interested in becoming this type of physicist, I think coming to such a laboratory is a fantastic opportunity, because you learn to work hard, you learn to collaborate with other people. And I think you also, coming back to these values that I mentioned at the beginning, the fundamental reason why we do science, the applied spin-off values, and then also these educational efforts. I think those efforts of mine clarified those values and why they are important to me.
So are you going to miss it now that your PhD is finished?
Absolutely. But I will also start working in a new scientific institute. I will start working at the Max Planck Institute for Plasma Physics in Munich, which I think will be quite of a similar environment, some underlying similar physics, but it will be, let's say, new geometries.
Do you know what's the topic, or what kind of research questions are you trying to answer at Max Planck?
So we're going to actually try to address some accelerator physics problems. So accelerator is a fusion reactor that would replicate a star on Earth, you can say, as the ultimate energy source. So what I will do will be to try to, let's say, numerically understand boundary conditions and the geometries of the accelerator, actually with methods similar to what I've been using now, although now it's a particle accelerator, but there will be a accelerator. I don't know all the technical details of the job yet, but I think there will be another very interesting sort of replicate some grand scale universe process here on Earth, and hopefully for a good cause of finding the ultimate source of green energy.
Wow, that's very interesting. Thank you so much for your time. I really appreciate it. And thank you for the very nice metaphor as well. I know that usually the fans of Space Bites like the metaphors because it helps them understand things better. It was a pleasure to have you on the podcast today.
Yes, I hope I could provide some answers, but I think the questions are always more numerous than the answers.
Yeah, honestly, as you're talking, I keep thinking of more questions, but unfortunately we're very limited on time. So yeah, thank you again.
Thank you.